Hey guys, I've been getting a lot of questions about this problem from part two, and I just wanted to take a second to go over it. So, if you read through the problem, you'll actually notice no mention of half-life or doubling time or anything like that. And what you'd recognize from that's true. We don't need to use that here. And so let's figure out what we do need to use though. It says we have this program that's reducing infant mortality at a rate of 8.7% per year. So what does this sentence just tell us? What's this rate decreasing like? Is it decreasing like a linear function? No, because that's a constant rate. Since it's giving us this percentage change, that's telling us the relative rate of change is constant, which means it's going to be fitting into our exponential decay formula. We could use either one here. I'm going to use p equals p0, our initial value, times a, which is kind of our growth factor, to the power of t. All right? And so the question is, given this rate, how long is it going to take for infant mortality to be reduced by 38%? So first question is, how do we start filling in some of this formula? Do we know our initial value? Not really. What about this a, though? This a is kind of like how fast things change, right? And if you remember the formula, a equals 1 plus r, this is telling us our growth factor is equal to 1 plus our relative rate of change. And so you might think, oh yeah, I have that right here. I can just make a equal to 1 plus 0.087, which is equal to 1.087, right? But that's actually not what you want here, because it's telling us it's decreasing by this percentage per year. So you'd be really close if you did this, but you need to make this a minus here. So we'd make minus, and then that's wrong, and so we'd plug this into our calculator to get that a is equal to 1. Not 1, sorry. Point 913. Okay, so now we know our formula looks like this. It looks something like this: p0 times 0.913 to the t, right? And so all I've used so far is the fact that I know this is growing in an exponential fashion, that I'm using my exponential decay formula, and I've just inserted this 8.7%. Now, how do I answer this part of the question? How long to be reduced by 38%? Now, just very generally, this is saying I'm going to have to solve for this time. This is the thing that I'm going to have to be figuring out, right? And now, so what's this talking about? How long until it's reduced by 38%? Well, that's actually talking about the output. It wants to know when this p is a certain value. And what value are we actually interested in? Well, it doesn't tell us exactly, but it tells us we want the initial quantity to be reduced by 38%. So think in your mind, maybe if this was be reduced by 40%, we would actually want 60% of our initial quantity. That's what we'd be looking for our output. But this is 38%. So what we actually want is 62% of our initial quantity as the output, right? That's what we want to figure out. We want to figure out the time when p is equal to this. So that's the thing I'm going to change. And if I start solving for this, I notice that these p-zeros cancel out. I'd have 0.62 equals 0.913 to the t. How do I finish solving for this? Well, where is my variable? It's in the exponent, right? So we have a special rule for whenever something's in the exponent, we have to use ln's, right? So we take the ln of each side. The ln of 0.62 equals the ln of 0.913 to the t. This t would come down, right? So I'd get ln of 0.62 equals t times the ln of 0.913, and then I could just divide each side by 0.913 to get t. Hope that helps.